In mind, I'd like to introduce our guest of honor to you today. Dr. Reber was born in Chicago, Illinois, December the 22nd, 1911. And I want you to note that today is his 76th birthday. So happy birthday, Grote. Grote obtained a Bachelor of Science degree at Illinois Institute of Technology in Chicago in 1933, and he was later presented with an honorary doctorate by the Ohio State University in 1962. In the middle 30s, he worked as a radio engineer in Chicago for several radio manufacturers. Although Karl Jansky discovered the existence of radio emission from the galaxy as early as 1932, fully a decade passed before the scientific world began to take a real interest in this discovery. And during that barren period, one man, and one man alone, compelled by a great love of science and interest in research, carried forward the work that Jansky began. With his own hands in the summer of 1937, and that's our 50 years, Grote built and operated a 31.5-foot diameter paraboloid antenna in his backyard in Wheaton, Illinois. And he persisted over a number of setbacks in attempting to observe this radiation that Jansky had described 10 years earlier. His efforts were indeed crowned with success when in the spring of 1939 he detected radiation from the Milky Way at 160 megahertz. He went on to make the first maps of the radio northern sky, and this work that Grote did was crucial in pushing forward the subject of radio astronomy at a time when he indeed was the only person working in the field. It's a great pleasure for me to present to you Dr. Grote Reber, who will address us on the topic, the Wheaton 31.5-foot paraboloid construction and first measurements. Grote?
Well, I'm supposed to talk about myself, and I find this sort of embarrassing. So first I would like to talk about my eminent predecessor, one Karl G. Jansky. He was born in 1905. And I'd like to have the first slide, please. And that picture was taken in 1933 when he was 28 years old. And the second slide shows his merry-go-round. This is a rather large device. It's 100 feet long and about 18 feet high, and picks up radio waves perpendicular to it and turned around the horizon once every 20 minutes, and the output was fed into a recorder. Now, he found that there were some atmospherics, but nothing like what's on the long waves. So we can turn the lights on again a moment. And most of the time, the recorder didn't draw any atmospherics because there weren't any. So it should have drawn a straight line, but it didn't. And there were little wiggles on this line. And these attracted his attention. And at first he thought they were some kind of interference over the hill, but they didn't turn out that way. It turned out that when they first were recognized, they followed the sun. That is, they appeared in the east in the morning, passed through south at noon and disappeared in the west in the evening. So they must be connected with the sun. And he writes this up. But before he can get the thing to the publisher, they've already changed some, and he attributes this to the fact that the sun is rising earlier because they moved to the east. And then there's the usual stumbling around, and when the results finally come back to from the printer, the proofs, it's now the 15th of May, and he decides that this idea of connecting with the sun is no good, because now they're crossing south at 4:30 in the morning. Well, he writes several papers about this. And he shows some graphs, and sometimes the graphs do this, and other times they do this. And this is a great mystery. In other words, it changes from this pattern to that pattern in 6 hours, and then 6 hours later it changes back. All very mysterious. Finally, he sorts the thing out and comes to the conclusion that these radiations do not come from a single source, but come from a variety of sources, and that these are connected with the Milky Way. This goes on over a period of several years. And finally he says, a more detailed analysis of the data has shown that every time the antenna points towards some part of the Milky Way, the record shows an increase in the energy received. And also, every time the record shows an increase in energy received, the antenna is found to be pointing towards some part of the Milky Way. So it's connected with the Milky Way. Now, the most obvious thing associated with the Milky Way are the stars, and the sun is our star, but he is dumbfounded that he can't find any radio waves from the sun, which should be much stronger than all from the Milky Way combined. And so then he has another great idea, and finally comes to the conclusion that this radiation's got nothing to do with the stars, but is most likely connected with the material between the stars, particularly these charged particles. If the radiation comes from such particles, one would expect the response obtained to depend upon the directional characteristic and the gain of the antenna and the way it is pointed relative to the Milky Way, and an expectation which agrees with the observed facts. I read these papers recently all over again, and I found it an inspiring piece of scientific sleuthing. And it's pretty obvious after reading them these many years what it was that attracted me to this subject. This man had gone out of his way to investigate a subject which really had no practical merit. It was so faint it had no use even as interference as far as the communication system was concerned. So, well, I was employed at the time and as a radio engineer in companies in Chicago. And I'd been doing amateur radioing, so I thought, well, this had great possibilities. And I contacted Jansky, and they weren't going to do anything more. And I tried Harlow Shapley at Harvard. They knew about it, but they weren't going to do anything. And Otto Struve at Yerkes, and a fellow named Langer at Caltech. Everybody knew about it, but nobody was going to do anything. I tried Walter Barkey, Dean of the Department of Physical Science at the University of Chicago, and he was very well aware of it, and he was dead sure Jansky had made a mistake. It couldn't possibly be so. And that the evidence was some, well, aberration. And he had a very good reason. According to Walter Barkey, the ionosphere was a mirror which reflected man-made radio waves back to the Earth around the curvature of the Earth. And this mirror was silvered on both sides. And so any celestial radio waves would be reflected back into the sky. He was right, but he was wrong on the wavelength. I also contacted Henry Gordon Gale, who was head of the Department of Physics. And he was an old man when I was there, but in his younger days, he was an able and effective assistant to Michelson, so you can guess where he stood. As near as I could make out, Gale had never heard of this, and he didn't want to hear about it. So I thought, all right, if nobody's going to do anything, maybe I'm the guy to do something. So I considered the whole matter. And you have to remember that in that day, antennas consisted of wires, networks of wires, something like what Jansky had, and some of them very much more complex. And they were highly resonant. They would only work at one discrete frequency. And if this investigation was going to be any good, it was going to have to work at a lot of different frequencies over a wide range, 10 to 1, 50 to 1 maybe. And this meant that if any given antenna system composed of wires were built, it would be only useful at that one wavelength. It would be then necessary to demolish the whole thing and start all over again at another wavelength. So that was out. So then I thought, all right, if this radiation has got some characteristics of black body radiation, its intensity per unit bandwidth should increase as proportional to the square of the frequency. And so the higher the frequency, the more energy you should have to play with. Also, for any given size antenna system, the resolution increased proportional to the size of the system. So the obvious thing to do was to go to the highest frequency available at that time. Well, after all this cogitation, I decided the thing to do was to build a dish. And it's certainly not my idea. That goes back to Isaac Newton in the 17th century. Well, it had been used by many people throughout the 19th century, and the biggest dish that had been built up to that time was the 100-inch telescope at Mount Wilson. So I decided to try to design a dish. And what kind of a mounting should it have? Well, the Earth rotates, so we can take advantage of that to sweep out bands in the sky. And all it needed was an up and down motion like a meridian transit telescope. And it would produce pictures pretty much like a modern TV tube. It would sweep and sweep and sweep each time the Earth turned around. And then these would be put together and you'd have a picture. So I decided to build a dish. And the next slide shows, I think, a picture of me in 1936. And as you can see, there's been some change in the last 50-odd years. Now, before you jump into something like this, you try to find out where you're going. And so I built a model of the dish in 1936. And the next picture shows, the next slide, a model. This is about 6 inches in diameter, or a little more, and was put together out of copper wire. And it was going to have to be a pretty accurate dish. And therefore, it was going to have to be a pretty deep dish. And so this design satisfied those requirements. Also, the dish was available to work at any frequency over a wide range merely by changing one box at the focal point, which was very easy. So the next slide shows it tipped over to the side. And I decided on the basis of this to build a dish. So the question was, how big a dish? And the distance between those side circles is 20 feet. And the distance across there is also 20 feet. And that was determined by the longest timbers you could buy at the lumber yard. So the size of the dish was determined, or the mounting was decided by the size of the timbers you could buy in the open market. And the sheet metal then was ordered appropriately. So I personally cut and drilled and painted all the timbers beforehand, and the local blacksmith shop allowed me to come and cut up all the gusset plates to put these things together. And I got a little help from my brother and another fellow, and we put the thing together without the parapet one afternoon. And people came around that evening and said, "When did you put that thing up?" It was about the size of a small house. And I said, "Oh, well, we had nothing to do this afternoon, so we thought we'd put it together." Well, then we put up the parapet, and well, that must have been about in August, because most of September was, see, this started in May, and most of September was spent putting the sheet metal on. So, as I pointed out, that the shortest wavelength possible would be the good place to start, because it gives high resolution and presumably quite a lot of energy to play with. And being in the radio industry, I had connections, and the man from RCA comes around and tries to sell us radio tubes. And so I put the bite on him for a magnetron. And a few weeks later, he comes around again, and he has a nice magnetron in his pocket and says it is yours. So the next picture, the slide, shows some of that 9-centimeter test equipment. And that's the magnet for the magnetron. And the magnetron has wires that go out there, and there's a small lamp bulb at the end. And it would put out a watt or so at about 9 centimeters. And then this is a horn, a cavity resonator under test, and these different horns went on there. And the idea was to find a pattern, which it did quite well. You see, nobody had done much of this kind of thing before, and the obvious thing to do was to put some kind of a dipole with a reflector at the focal point, but that's not very good, because it has a lot of acceptance from the sides and some from the back. And I wanted some contrivance at the focal point which would look at the dish and only at the dish, and this satisfied that. I ran quite a few of these tests at different wavelengths, and the iron for the magnet and the coils for the magnet, and all this hardware was built by the Stuart Warner shops, and I am pleased to thank them at this late date. So that continued, and I built a small receiver, and it was just, well, I also had connections at the University of Chicago, and they built me a Barkhausen tube. Now, a Barkhausen tube is a triode with a grid running positive, and if you operate the thing suitably, it will oscillate. But as a detector, it's useless because it has tremendous shot noise. And then I had them build me a small diode with only a few thousandths clearance between the anode and the cathode. And transit time kills you there. So I finally ended up with a crystal, and I made a lot of tests with this thing, and it was possible to modulate this magnetron. And I fixed up a crystal in this cavity resonator with a pair of headphones, and I could walk all over the house and out in the yard and around. And the whole place was just full of standing waves. It was tremendous, because there was multiple reflections all over the place. So ultimately, I found a kind of a crystal which goes under the name of sphalerite. That is, it's a natural zinc sulfide, a yellow crystal. And no matter where you put the cat whisker on, lo and behold, it was sensitive. You didn't have to hunt. So I built a receiver with an amplifier on this thing, just an audio amplifier, high gain, and put it out on the antenna to see how it would work. And I didn't get much of anything except an occasional surge when there was a local electrical storm, which the same thing that Jansky was getting years earlier. And I tried the sun and the moon and some of the planets, and they were all failures. And see, the difference between Jansky's 14.5 meters and 9 centimeters is about 160 times. And you square that, and the intensity should be up 25,000 times compared to what Jansky had. But it wasn't anywhere near that. So it certainly wasn't black body radiation. Well, that was a failure. This was the latter part of 37, early 38, and so then about this time, RCA brought out acorn tubes. And I got a hold of some of these, and it was possible to build a regenerative detector and set it just below the oscillation point at a wavelength of about 33 centimeters. I think it was 910 megahertz, something like that. So then this was worked up with a larger drum. I think it was made out of a 5-gallon paint tin, which was about the right size. And it was tried. And I think the next picture shows my dish. Yeah, this is the one taken from the south, or southwest. And this is a little later. This has a big drum at the top. I have some pictures somewhere that show the same thing with the small 33 centimeter drum at the top. And incidentally, there was a hole in the center of the dish right there. So a secondary mirror could be put on for Cassegrainian operation in case you wanted to put the receiver down here, but it was never used that way. And the next dish shows, or the next picture shows a dish from the north. And as you see, it's clear to the south. So the location was pretty good. There was no obstacles in the way, all the way down to a pretty low level on the southern horizon. And you can see there's my cavity resonator. And that's 20 feet across there. Well, that was a failure tube. So Jansky had obviously found something at 14 meters, so by continually increasing the wavelength, I should ultimately come to some wavelength where I could find this stuff. Okay. About this time, I'm able to get some acorn pentodes, type 954. And I make some preliminary tests on them, and they seem like they'll do the trick. And they're pretty good up to maybe 200 megs. Beyond that, they pretty much poop out. So the frequency was going to have to be less than that, and it was going to require a big drum. So I contact Alcoa, and the biggest sheet of aluminum that's available, standard, is 6 feet wide by 12 feet long, 1/16 of an inch thick. And after some correspondence, it's decided they can roll one of these sheets into a drum just a little less than 4 feet in diameter and 6 feet long. And they make some welded on back end, and they make various apertures in the front with different size holes and so on. And the antenna's back in there, and the receiver sits on the top. This was all done for the princely sum of about $140. Have to multiply by 100 times a day. Well, I think the next slide shows me with the dish tipped over. Yeah. See, there's the receiver, and this is it tipped down at the service tower. And the ladder went down there. You had to have a removable ladder because I lived about a block from the school, and the kids would come and climb all over the thing like it was a playground. So with a removable ladder, they couldn't climb up high on the thing and get themselves killed. The overhanging feature of the dish prevented them from getting up on top and running around. So the highest they could get up was up underneath the dish. Well, let's see. Now, that is the first 160 megahertz receiver. It had 5 stages of these 954 acorn pentodes. And try the next one. Let's see what the next one says. Okay. This is one of the first successful tests. The receiver was started, and I would go down there after it had warmed up and take a reading on a microammeter every minute, and then record this in the book. And then these were plotted up. And what you see here this is time along there, standard, central standard, and this is amplitude. Now, the voltage that came out of the diode was negative, and it went into a DC amplifier. So the bigger the negative voltage, the smaller the output current. So amplitude is increasing downward. And this is the warm-up, and after an hour or so, it steadies out. And then the Milky Way goes by, and then after the Milky Way's gone by, it steadies out again. So this was very, well, reassuring, because it wasn't any little bits. You can see that the signal-to-noise ratio was 20 times or so. You didn't have to juggle around doing any statistical analysis of a lot of humbug. That it was, it was in there, see, and any fool can see it. You don't need to be a statistician. Okay, so quite a lot of time was spent. Now you see, up to this point, I'd sunk a lot of money and time and effort into this thing and hadn't gotten anything. So you're sort of loath to go overboard and buy a lot of expensive equipment until you got something to show. And this was it. Okay, now this receiver had a narrow bandwidth and some thermal instability, but it worked beautifully at night, as you can see. In the daytime, with thermal instability, it wasn't so hot. So the next step was to get this. Furthermore, I couldn't sit down there all night and take these readings and then go to work the next morning. Well, at least it was difficult. I wouldn't try it today. So the next, let's see, I have to look at this. So let's see what the next one is, the next slide. Okay, so another receiver was built with a broadband. This worked from 156 to 164 megs, about 8 megahertz bandwidth. And the antennas in the drum were changed from just a wire dipole to conical antennas to broaden it out, and the cover was taken off the drum. So the system had a much broadbander response. And let's see, I think this place will shift over to here. Let's see what the next one is, out of curiosity. Forget it. Oh, okay. I didn't realize that one's in there. I must have put it in recently. I ordered some stuff from Charlottesville, which came several weeks ago, and they said some things were going to be sent from Green Bank. And they got here about 20 minutes before the line. So I hadn't had a chance to put these last pictures in properly. Anyhow, that's the setup for automatic recording. And there's an Esterline Angus recorder. There's my signal generator for measuring the signal receiver accurately, a DC amplifier to drive that, power supply, and it worked very well. It gave no trouble and ran hours and hours and days and weeks and months and even years. I don't recall it much of anything had to be changed because the tubes were operated well below rating. You get better stability that way. They don't get so hot, and they last longer. The emission isn't used up as well. And if you run a below rating, then you don't have to try to squeeze the last ounce out of them, and they got a pretty long life. Well, now, these are some of the automatic drift curves. And you can, this just goes, where the plane of the Milky Way goes past, and there's a P, the plane of the Milky Way, and another one, and so on. And these are standard nighttime curves, and you can see they could be read very accurately to a few percent. And this last one I put in on purpose because it was a local electrical storm, and you notice the spiky nature of the interference on there, but they're very rare. I only maybe had a half a dozen of those at the most. So there was oodles of this kind of information, and it was possible to draw up a map. Now, this receiver had stability, which the previous one didn't have, and so it was possible to use it in the daytime. And so I tried it on the sun, and much to my dumbfounded amazement, well, see, I set this thing going before going to work, and then set the end dish for the proper elevation angle, and then the sun would go by, and I came back in the evening, and I'd have a record. And the first time I tried that in the sun, the pen went off scale and stayed off scale for about a half an hour before it came back down. The sun had an intensity far beyond anything anybody believed. Because at 6,000 degrees, it should have made just maybe a quarter of an inch rise on the tape. But it didn't. It went way off. So I backed the gain off about 10 dB and tried it again. And it again went off scale, but didn't go off so far. And the third time around, I got the gain backed off enough so it stayed on scale. That was about September '43. And the sun was pretty uninteresting. It did the same thing every day. And these are some of the drift curves. And this is the sun, and that's the Milky Way. And as time goes by, you see the sun gets closer and closer, and here it's practically coincident. Apparently that's the 16th of December. And see, there's the sun, there's the P. Now, a week or so later, there's the sun, there's the P, and then they separate, and there's the sun and the Milky Way, and so on. So this is evident why Jansky got the wrong idea. That is, he detected this or recognized it first in the latter part of December 1931, when the situation was this. And they were coincident. The sun was in the Milky Way, and he thought it was the sun when he was picking up, but actually he was picking up the Milky Way. Well, that went on, and let's see. Okay, the next slide, please. Well, a map of the sky was made at 160 megahertz, which I will get to later. And I had a pretty good grasp on the thing now. That is, it was evident that the intensity was inversely related to frequency instead of directly. But by going to a higher frequency, it had greatly improved the resolution. And so an attempt should be made, and 2 to 1 would be good, but 3 to 1 would be much better. And so the next effort was made at 480 megs. And you had again start from scratch, no signal generator, nothing. And I got a hold of some tubes which were fobbed off on me by RCA, because RCA thought they were great. And they were called electron beam multipliers. They had a tremendous transconductance of about 60,000 micromoles. And they had what the name says, an ordinary triode, and the output of that, instead of going over to the anode, went through a couple of electron multipliers. And that gave it this tremendous transconductance. But it also introduced huge shot effects. And electron multipliers were very anemic and they wore out rapidly. So the tubes only had a life of about 100 hours, and they were very expensive, and the whole thing was a failure. I don't recall that it was hardly even, it was tried a few times, but I didn't get anything. So about this time, I was in a position to get a hold of some General Electric 446 speed lighthouse tubes. They were trials, and very good ones. And so this receiver was built to take advantage of it. There's a push-pull input stage from a balanced antenna, then there's a transfer from balanced to unbalanced, and then there's 5 more stages up the line to a diode. And these things, hold on, get tangled up here. These things were so good that they oscillated. Anytime you have a high gain amplifier, it's likely to break into oscillation. And they operated grounded grid. And this is the cathode, and it went out to the input circuit. And this is the anode, and it went out to the load. The feedback goes from here. In other words, there's a little capacity from the plate to the cathode, about 1/10 of a puff. But 480 megs, that's quite a bit. And that would make the thing oscillate. So I got out some books on circuit theory, and I found that if you break this and put in a little inductance in here, and you portion that properly, you can get that to cancel this so that it looks like an open circuit across there. So I did that. And there are little projections sticking out there, and those are the plungers that you run in and out to adjust this inductance. And it has limitations. That is, it won't work over a wide range of frequencies because they're both frequency sensitive, but over the 8 megs that thing covered, it was plenty good. So that ran again, and another set of contour maps were made. And I want to finish this up before, see, this can go on and on and on. Let's take a look at the next slide. Oh yeah, there's the focal point equipment for 480 megs, that hemisphere. And the next slide. Oh yes, okay. This was going by about 1945 or early 46. Well, after the war, immediately, within months, Van der Hulst showed up at Yerkes as some kind of a visitor. And so they brought him down to look at my gear. And he gave me a discussion about this 21 centimeter line, which theoretically was due to a transition in the neutral state of hydrogen. He tried to explain it to me, and all I got out of it was that you got 2 vectors like this, and I forget which way. Anyhow, this is arranged so that you have more energy, I think, in this state than when you have it in the state where the 2 are going in the same direction. Anyhow, this transition would occur. Presumably, it gets knocked out by some mechanical means, and then it falls back of its own accord and radiates at 1,420 megs. So I asked him where he could look for this, and he said, oh, well, he didn't know. It would probably be the center of the Milky Way, which, of course, is a good guess. So then I asked him whether it was going to appear in emission or absorption, and he had the faintest idea. It was really a little better than an idea. And at that time, it looked just barely possible that something might be done. So the lighthouse tubes weren't going to do it, but I found some other tubes. I think they were made by Raytheon that looked pretty promising. And again, there was no test equipment, so the first thing to do was to build a signal generator. That's a 1420 meg. I think it went from about 1200 to 1600. And a wavelength, a wave meter there, which was tuned by this knob, which ran the lengths back and forth. Not highly accurate, but good enough. And the next slide shows the receiver, and there's one of those tubes I mentioned. And they fit in this series of cavities, and there's a double diode goes in the output. I forgot what that is. And there's another cavity. That's 6 inches. So you see, it all got pretty small. And the next slide. Yeah, this is the focal point equipment, but it was never used. It was just set up. And I think that's as far as I got. What's the next slide, if there is one? 2 more? Oh, several more. Okay. Oh, yeah. How are you going to find the line? You got to have something tunable. And this I got from military surplus. It's an echo box used in tuning up radars. And it has a very narrow bandwidth, about 30 kilohertz at 14 megs, 1420 megs. And so the idea was to put this into the system and turn that center knob until there was a rise or a fall, in which case you'd find this line. But it never got that far. Now the next slide. Okay, so much for that. It was never finished. But what we know today, it probably would have worked. Now, the material was turned over to the National Bureau of Standards when I left Wheaton in 1947. And it was used there for a while, and then they picked up themselves and went out to Boulder, Colorado. And the dish was dismantled and taken out there, but never put together. And then when Green Bank was established, the arrangements were made to get all the pieces back. And so I was there during the summer of 1960 and helped put this thing back together again. And they seem to take great pride in it. It's much better condition than when I had it back in Illinois. And they painted it, see, red, white, and blue. And the next slide shows it in I guess, the stow position. No, it's from the back to show all the rib structure. See, it was quite complex. I think there was something like 72 ribs around there. And half that number in there. And there's a 6-foot man. And the turning mechanism is the rear axle of a Model T Ford truck. See, when that was built, Model T cars were plentiful in the junkyard. You could get any amount of them you wanted for next to nothing. But by 1960, they were long departed. So I thought, okay, if it's a good idea for them to have this as an ornament, well, I'll go on a little more. People say, in Wheaton, the dish was on a meridian transit mounting. Here, it's on a turntable. How about that? Okay. The situation in Illinois showed that this was going to have very sensitive equipment. And the main interference was man-made, mainly automobile ignition noise. And about that time, Yerkes Observatory took over the operation of MacDonald Observatory at the University of Texas. MacDonald had given the university a lot of money to establish an astronomical department. And I talked to Struve, and see, this was about 1940, 41. I talked to Struve with the idea that if a move was going to be made, the thing to do was to move this dish down to Texas, the lower latitude. You wouldn't have as much severe weather. In the wintertime, the snow would sometimes lock that thing up, so you couldn't move it. And if it was going to be done that way, then the thing to do would be to put it on a turntable, because it would greatly increase its usability if we were out there in the desert somewhere. And so the turntable was built and put together and tested, make sure it was all in running order, and then dismantled. And it was stored in my garage during the war And then after the war, it was gotten out and put together first at Sterling, Virginia, and then later at Green Bank, West Virginia. So that explains the turntable. While I was there at Green Bank, putting this together, it occurred to me that it would be nice if a reproduction was made of Jansky's original merry-go-round. And so I got a hold of Southworth and broached the problem to him, and he thought it was a good idea too. So he took it up with the powers that be at Bell Labs, and they thought it was a good idea, and so they decided to make a reproduction of Jansky's original merry-go-round and install it at Green Bank. But Jansky's antenna was manufactured in 1931 or maybe 1930. And as I say, there were lots of parts for Ford automobiles. And he used 4 of the front axles and wheels. But there were none to be had, long gone. So I thought, all right, we're way out here in the boondocks. So I would put an ad in the Marlington newspaper, which I did for the farmers, inviting them to come forward with any front axles and wheels of Model T cars. And lo and behold, there was a lot of them laying around on the outback that hadn't yet been gone to the junkyard. So we got an ample collection of front axles and wheels for reproducing this dish. But what are we going to do for tires? Now, what do you know? We looked in Sears Roebuck's catalog, and apparently there are a lot of automobile buffs that rehabilitate ancient cars, and there's enough for the Sears Roebuck to have the right size tires. So we bought brand new tires and put on these ancient wheels and axles. And there was one more catch. Of all things, it turned out that the head of the carpenter shop that built the original one 30-odd years earlier was still there, see? And he could see how it could be made better. That is, the second time around, he could greatly improve on the design. But they didn't want that. They wanted it the original way. So they had trouble with the carpenter because they had to impress on the carpenter that this was historic and that it was supposed to be done like the original. So ultimately it got down there and was put together. Well, is there any more slides? There's one more. All right, see what the last one says. Well, this is out of order. Somehow it got confused. This was my first control panel with the dish for operating at 160 megs. And that was the receiver, which ultimately went out on the end of the drum. And that's the microammeter I used to sit and watch and record the output every minute. So that's all still in existence. Someday I'll donate it to some worthy institution because I'll never use it again. So, ladies and gentlemen, I think that explains where we stand. Thank you. This is supposed to be question and answer time. And I will listen to questions, but I won't necessarily give an answer. However, if somebody would like to get up and say a few words, I'll be happy to listen. Yes.
Could I show just one view graph?
Sure.
Which was, I think,
Oh yeah, I'd forgotten that thing.
well, maybe you can explain it better than I can.
Well, yes. These are the contour maps that we were talking about. And that top map is my rendition of Jansky's data. He got the data in 32 and I renditioned it about 47 or 48. And that's his beam width. So you can see in a general way, it did connect with the plane of the Milky Way. This fuzzy stuff is the optical part of the Milky Way. The next map is what I made and published in 44. Data was taken in 42 and 3. And you can see that he's right. It does connect closely with the plane of the Milky Way, and that's the antenna beam. And as you'd expect, the resolution greatly increased, and there's Sagittarius, this is Cygnus, Cassiopeia over here is in Taurus, and down there is in Puppis. And that's the supernova remnant, and this is some other well-known radio source. And then Hay Parson Phillips did the same thing at 64 megs, but they had a big beam. And it gives the same general idea. And Sanders at 60 megs at 48, it gives the same general idea. And then this is yeah. This is the 480 megs in 1948, and there's Sagittarius, and there's the northern spur, Aquila, and this region there splits up into two, and I think that's at Cygnus X1. I don't know what that thing is. And then it repeats again out here, Cassiopeia, and the beam width you see is very small. And then this region up in here splits up into two, and that one is the Crab Nebula dead on, and I don't know what that is. So I folded up operations there in 47, so this was taken in late 46 and early 47. In any case, what it tells you is you already know that if you have more resolution, you get better detail. And since then, the resolution is increased by another 2, 3, 4 orders of magnitude. And we'll hear about that this afternoon.
I might say that this interesting collection of maps does have a Canadian connection that I found in the Journal of the Royal Astronomical Society of Canada. In fact, it was an attempt by two people, some of us older people in the audience will know, Ruth Northcott and Ralph Williamson have done that observatory to try and see the connection between the radio maps and the Milky Way. It was Ruth Northcott who made those particular plots and all the symbols where the planet of the Milky Way and Northern Star is.
Paul, I know it took a long time for you to become respectable. I'm holding here a copy of the Astrophysical Journal, volume 100, from 1944. And there's an article by Grote Reber on cosmic static that shows a number of the things that we've been shown now. But during the period that it was difficult for you to become respectable, I'm wondering why, although people like Struve and other eminent people at the University of Chicago and elsewhere were not paying a lot of attention to you, why didn't the 4F graduate students who were still left around during the war, why weren't they beating a path to your door, or to your backyard?
Why wasn't what?
Why weren't the graduate students who weren't taken into the war coming to see you?
Well, I think most of them were, but you see, I was older. And before going back to the university, I had worked in various industrial concerns. And my outlook on life was rather different. Too many of these people in universities start at kindergarten and they end up as senior professor, and they've never seen anything except the inside of an educational institution. But my outlook was rather different. And so I was in a very preferred position. And that I was employed in a place where the facilities necessary were there. My superiors looked upon my activities with benign ignorance, and I could get things made in the shops, and I had connections with the rest of the industry through the various salesmen that would come around. And I lived in a suburban town, which at that time was quite small, and there wasn't much electrical interference in the beginning. And there was, as I pointed out, a clear southern horizon. So everything was in my favor, pretty much like everything was in Jansky's favor, that he was the right man at the right place doing the right thing at the right time. Pretty interesting. See, he worked there in the early 30s, which was a solar activity minimum and a pretty low one. If he'd been 4 or 5 years earlier or 45 years later, he would have never found it because the ionospheric contortions would have so confused the data it would have been practically impossible to fish it up.
Could I give a comment on this? And that is that, see, I spent some time at Jodrell Bank, which is part of the physics department in Manchester. And in the physics department, we used to say, what's level doing out there? Oh, that's radio, that's electromagnetic, that's not physics, that's electrical engineering. So it seemed to me that physicists wouldn't accept radio astronomy in those days. And then the optical astronomers were so dyed in the wool that they wouldn't admit to radio astronomy. So I have a feeling somehow that radio astronomy fell between two stools. It wasn't until things really started developing, and a lot of it developed in electrical engineering rather than in astronomy or physics.
Well, aside from a couple courses that I took at the University of Chicago in astronomy, I had no astronomical training. But little I picked up pretty much on my own. But I knew immensely more about astronomy than the astronomers knew about electrical engineering. And consequently, there was no meeting of the minds. And you have to remember that the thing as complicated as a photocell and a DC amplifier and a microammeter were a mysterious black box to the astronomers. They couldn't understand them. Anything that connected with vacuum tubes and tuned circuits and that kind of stuff was hopeless. They didn't even know the words. So that's what it amounted to.
I'll ask another one then. Now, I know you managed to publish the first paper in the literature on the detection of the radio sun.
Yeah.
Because a number of people, both in Germany and in England, who had detected it accidentally were prevented by wartime restrictions from publishing. But I'm wondering, why did it take you as long as 1943 to detect the sun? I would have guessed that with that equipment you would have found it right away.
Very true. Lethargy and too much knowledge. That is, the sun, according to the astronomers, had a corona sun or a photosphere of some 6,000 degrees. And I could compute what 6,000 degrees was going to be, and it was only maybe about 3 small divisions on those records. And the first receiver was absolutely hopeless because of thermal instability. The second receiver might do it, but during the daytime when the sun was around, there was these tremendous automobile interferences. And consequently, it was going to be difficult to fish the thing up, the sun up, with all this automobile interference. However, it still might have been done on a weekend or something like that. And so, well, it just was put on the back burner, and nothing was done until I tried the second receiver a couple of years later. In retrospect, it could have been fished up 2 or 3 years sooner, but it just didn't get around to it, that's all. Incidentally, there's some differences here. The English did detect the sun, I think about 1942, but they didn't detect the quiet sun. They detected these surges. And it turns out that the Germans had some equipment on the western coast of Denmark as early as 1940 for surveillance over the North Sea. And they found these surges too. I forget the frequency, it was fairly low, about 120 meg or something. And they had an interesting antenna. It was not a mechanical thing, but they had a big concrete wall. And on front of this concrete wall were a lot of dipoles. And they had a mechanical phase shifter that rotated around. And this phase shifter swept the beam back and forth like that. It was plus or minus about 60 degrees. to the surveillance. And with that, they could easily and quickly detect where this stuff was coming from. And then Southworth found the background sun at centimeter waves about a year earlier than I did. And he wanted to write something about it, but these military nuts said that this is giving away secrets, and they wouldn't let him. Then when mine appeared in print, he went back to the military blokes and said, look, the cat's out of the bag, you better let me print it. So they finally did, and he published it in the Journal of the Franklin Institute, I think a year later. Something like that. I don't have much use for these secrecy boys. Well, I'll tell you, very recently, see, I go out to CRC, that's your Communication Research Center, which is one of these secret installations, and you got to have badges and escorts and all this other junk. And there's a small bus. It goes back and forth. And I was waiting there in the guardhouse for this bus one afternoon, talking to somebody or other. And I don't know how the subject came up, but there was all this secrecy junk. And I said, the reason things are secret is so people can't see what's going on. And the guard busted out laughing because obviously his interpretation of what can't see going on was different than what the secrecy was for. It's still with us.
This is the first time I've met you, but I've had a bone to pick with you for a very, very long time. I started off at a little place called Jodrell Bank, and we started off on radio detection of meteors. And then Lovell gave me we built a fixed paraboloid straight up, and Lovell kind of said, well, there's this new idea of radiation coming from outer space. We're going to make 100, how big it was?
250 foot days.
150 with 180. We'll measure a strip of sky at 72 megahertz, and then we'll change frequency, and we'll get the spectrum of it, and that'll give us some idea of what it's all about. Well, the first part, I did the 72 megahertz, that was all right. But then I looked up some of your early work, and I said, oh, well, the signal is quite strong. I just need a straightforward receiver. I don't need this switching thing that Val has been bothered about. And so I set this up. And all I got were large, when it looked like rain, all I got were large drifts in the level. You were, I think your first measurements were something like a factor of 10 out. I often wonder why you didn't use 3C286 or something like to do better calibration. I never did finish my thesis, or my thesis project.
About the calibration level.
And incidentally, it was 100 round. It took him about 3 or 4 years before he finally got that system working.
I use a signal generator calibrated in microvolts. You don't worry about thermal stuff and all that jazz. And if you look at my contour maps, it's so many microvolts above, so many dB below 1 microvolt per meter and so on.
I'd like to know how the word cosmic, the noise got into the literature.
I don't know. I think maybe I dreamed that thing up for want of anything else. Because Jansky never used that term. But you see, he always talked about extraterrestrial origin. But once it was determined that it really was from outer space, it was cosmic all right. See, it's a much better thing. That is, what we are dealing with here are really cosmic rays. That this term cosmic ray got itself associated with a particle. But they didn't know that at that time. See? But you can't use cosmic rays for this because the term has already been used up. So, by the ignorant. So I had to dream up something else. So I call it cosmic static. I think that's what it amounts to.
I'm wondering why. I know that Jansky decided not to pursue his discovery in the late 30s when he had perhaps an opportunity. But when Jansky saw what you were accomplishing with a better antenna, did he get in communication with you? Was he in any way moved to?
I met him a few times. He was a rather slender person, not as tall as I am, and appeared to be aging. And I remember one time we were both at a conference in Washington, and I think it was the agriculture department. It was a big building facing Constitution Avenue, just east of Pan American Union. I think it's 20th Street. And it had to do with frequencies. And it was a big political conference on who was going to get what frequencies, and neither of us had any business being there. And so I suggested that we have lunch together and talk about something interesting. And he agreed and said that he had arranged to have a meal cooked without salt at a certain particular restaurant 3 or 4 blocks away. And so we went up there. And he ordered out his special meal, and I ordered off the ordinary menu. And we discussed things of mutual interest. And he told me at that time that being an engineer, his thinking was pretty much the same as my thinking. And that this feature of having it sweep around the horizon was a good idea for what the thing was intended for, but for astronomical use it certainly was not. It made the data too difficult to reduce. And if I remember, his words were that he had drawn up a proposal for a dish 100 feet in diameter with a 0.4 ratio to be worked at 5 meters wavelength. And he had sent it up the line and it had become lost. Well, not surprising. There was no reason why Bell Labs should buy something like that. That is, they might just as well start subsidizing pagodas in Burma or circuses for the Hottentots. And if that kind of a thing leaks out and the stockholders find about it, the president's liable to swing. So naturally, it didn't get anywhere, and it shouldn't have. That is, now, you're probably going to ask the next question. That is, there's this rumor that got bandied about that we're running over time, way over time, that Friis, Jansky's superior, prevented him doing anything more. And this is attributed to one John Pfeiffer of New Hope, Pennsylvania, who wrote a book. And these writer people are desperate for something sensational to put in their book. And Pfeiffer dreamed this up out of thin air. If you read the record, it is precisely the reverse. This phenomenon that Jansky had discovered was useless. It wasn't even of any importance as far as interference was concerned. But Friis kept him on for 5 years, paying his salary, while Jansky piddled around with this useless thing. And he allowed Jansky to buy certain small items out of the engineering budget to continue his piddling. And I'm sure that Friis frequently looked over Jansky's shoulder and was impressed. And Friis covered Jansky and, well, interceded for him in a benign and discreet manner which would not bring down the wrath of anybody's superiors. So instead of stopping him, I'm sure that Jansky was able to carry out these researches over these several years because of Friis, not in spite of.
Time for one more comment. And Karl.
I'm curious, did Jansky ever express to you one way or another his support or lack of support from Friis? Or his ability to pursue the research, or his lack of interest in doing it?
Well, he didn't discuss these matters with me. I only brought that up because of this silly rumor organized by John Pfeiffer. And a couple of times I saw Jansky, we didn't discuss any of that kind of thing. As a matter of fact, he was gone by that time.
This meeting that you referred to, when did that occur? When you had lunch together with him in Washington? What year was
Yeah,
that?
I saw him once at the electrical engineering conference in Chicago for a few minutes, but that was all.
What year?
Oh, must have been about 1935 or 6.
And at the Commerce Building, what year was that? When you saw him at the Commerce Building,
Well, that was later. That must have been about 1945 or 6. Because he died in 1950. Well, we'll worry about it some other day. Thank you.
Well, on behalf of all of us, Grote, I'd like to thank you very, very much for the personal reminiscences that you presented us with this morning. It certainly makes the subject come alive when you have someone who was involved right at the heart of it, giving his own recollections. Thank you very, very much. I might just comment that in his later years, Grote Reber has done quite a bit of work at the very lowest of frequencies. And a few years ago, when he was visiting Canada, he happened to notice a field of wire and telephone poles out west of here at a place called Ashton. And he decided that based on his knowledge of the best places to do low-frequency astronomy in the world, that Canada, given the existence of this field of telephone poles and wires, was a great place to come to do low frequency, around 2 megahertz, radio astronomy. And so Grote has spent a couple of periods with us here at the Herzberg Institute preparing this array at Ashton to attempt to do observations at a frequency of around 2 megahertz. At this point in the proceedings, I'd like to ask Paul Feldman to describe for us the arrangements for coffee.
Very simple. The coffee's right outside now. And I will run downstairs and bring your muffins, which are now ready. And Karl, can you give me a hand with that? We'll have everything in shape in 2-3 minutes. Free now.
We'll break for coffee.
Very good.
Everybody go through these stages, and again, you start there, touched on your mind.